Okay, at the end of the last video, I just finished a linear regression. I've left it on the screen here just so you can remember what we were up to. Before that, we had entered our data, plotted a scatter plot, and then we tried to fit a line to it. And clearly, if you look at this line, it really doesn't fit the data at all. So in this video, I'm going to try to fit a quadratic model to it. And the way I'm going to do that is by performing a quadratic regression. So just like for linear, we first click Stat. We want to go over to the Calculate menu. So we scroll over. And now we're going to do a quadratic regression, which you can see right there is the fifth. So I hit 5. And we're going to enter exactly the same series of steps that we did last time. The first thing we're going to do is we're going to tell it that our independent variable is L1, comma. Our dependent variable is L2, comma. And now what we're going to do is we're going to give it a function name. And typically you're just going to use y1. In this case, however, I'm going to do all 3 regressions on the same set. So rather than y1, I'm going to call it y2. Again, to do this, you click vars. You scroll over to the y vars. Select function. And here's y1. We've already created a function out of y1. So instead, I'm going to scroll down and choose y2. I hit enter, and I hit enter one more time, and there it is. So just like that, I have created a quadratic model for this data, and you can see here it's in y equals ax squared plus bx plus c form. That's the standard form for a quadratic. And down here, what you'll notice is our r squared value. Now again, to get a better idea of what this tells us, we multiply it by 100. And if we multiply this by 100, we get 83. So this model fits the data with 83% efficiency, I guess you could call it that. But really, it's all about confidence. So we can be 83% confident that this is a good fit for this data. What I'm going to go ahead and do, again, I'm going to pause the video while I write out this equation in ax squared plus bx plus c form, just so we can take a look at what it should look like. Okay, so there is my quadratic equation. I've just got the mouse hovering over it here on the right-hand side. And again, you can take a look. You can see the a value here, negative 27,763, which I've rounded a little bit from here just to take off that decimal. And the b value, 158,435. I rounded that again. And here it is. It pops up right with the x, which is where the b value should be. And then plus our c value, which, as you might remember, is our y-intercept, or our initial value. And in this case, it's 2,596,320. And again, that comes from right here. Now, if we go back to the graph, we can actually take a look at how well this model fits the data. So there's our linear. It's going to come in first because it's y1. And here comes our quadratic. Okay, so the quadratic comes in. And obviously, you can see the quadratic does a much better job of fitting this data. Specifically, what I want you to notice is right here, the initial value is actually quite close. You should also notice that the quadratic, the model here, its initial value is slightly below the initial value of our actual data. So if we go back to the data, we should find that this initial value is a little bit smaller than the initial value in our table. And if we do that, we see that our initial value here is 2,622,000. Whereas our initial value here is 2,596,000. So the difference, I mean, it is 25,000, but in the scale of things that we're working with here, it's not that much of a difference. So again, we can see here that the quadratic model fits quite a bit better than the other. And if we just hit second and then quit, it'll get us back to where we were. And again, the r squared value, 83%, tells us that this is definitely much better fit than the linear model. The last thing I'm going to do is I'm just going to alter my equation to make it fit the context. So our dependent variable, instead of y, we're going to use c for number of crimes. And wherever there's an x, we're going to replace that with t for time in years since 2001. And if we plugged in 0, that would give us our initial value, which would be the number of crimes in 2001. Finally, what I want to do is I want to perform an exponential regression on this, because I think after 2 times through, I should be able to go through it quite a bit quicker. And again, looking at this data, we can tell right away that the quadratic is going to be the best fit. So running the exponential regression is kind of pointless other than for the fact that I would like you to see what it looks like and also what the equation generated should look like. So again, we're going to click Stat, scroll over to Calculate. This time we're going to scroll down until we can find the exponential regression. We hit Enter, and again, our variables, second L1, that's our independent variable. Our dependent variable is L2, and we hit comma again, and now we're going to create a function for this. We've already used y1 and y2, so we can go ahead and use y3. We hit enter again, and it comes up right away. So here it gives us our a value and our b value, and right here our r squared value in this case, multiplied by 100, 16%. So obviously this is the worst of all three of them, and if we take a look at the graph, first the linear will come in, next the quadratic, and finally the exponential will try to be fit to it. And the exponential, in this case, you can see it's sort of coming in alongside that line there, and that's because at this scale the exponential is actually going to look a lot like a straight line because it's been flattened out so much. So the exponential is definitely not the right fit for us here. Again, second quit to get back to where we were, and I'm going to go ahead and write out what this equation should look like for you. Okay, so here is our exponential equation, and it's y equals 2,687,191 times 1.007 to the exponent x. A few things I want you to notice here. First, this right here is our a value, or our initial value, and what you'll find is if you compare it to the linear, these initial values are actually quite similar. And if you go back to the graph, turning off the second, you can see that these two things intersect. From this, from being zoomed out this far, you can't even tell that those values are different, although looking at the numbers, they are slightly different. So this gives us the initial value of the exponential model, and this 1.007 tells us the growth rate. It's so close to 1, which means really it's not growing very exponentially at all. So this thing is very, very linear in terms of this equation, but obviously it still doesn't come very close to fitting the data. So we know that an exponential fit is not very good. The only other thing I'm going to do here is I'm going to change the variables to give them context again. So the number of crimes equals 2,687,191 times 1.007 to the exponent t, where t is the time in years since 1991. Now, what you could do from this point with any of these equations is you could plug in, for example, a different year. So let's say we wanted to know the crime rate for the linear model in the year, let's say 2011. So that would be 10 years after. So we'd plug in 10 here. And in this case, this value would be much larger than any of the others because the linear model continues to grow over time. In the quadratic model, what we can see happening, if we go back to the graph, is that this starts to drop down. So as we move forward past the values that we have, the number of crimes will actually decrease. So if we plugged in 10 for t here and here, we would find the number of crimes is lower than any of the other values. Again, you could plug in the t here in the exponential equation and solve for that. So that's really the idea here, is to take a set of data and generate equations that we can then use to make predictions about what happens in the future, or even what happens in the past. We could take this back in time by making these t values negative. And that's it. That's linear, quadratic, and exponential regression. Yeah, end video.